Hello, this clip deals with the makeup of the carbonyl group, or basically the C double bond O when it's present in a compound. All this clip is going to deal with is how the carbonyl group is constructed in terms of orbitals and in terms of some other details that you'll need to know and understand so that you can then understand the chemistry of the carbonyl group a little bit later on, and also things like how it behaves in certain mechanisms that we dealt with separately. So let's have a look at the chemical makeup of the carbon double bond oxygen. Now, of course, we know it's a carbon atom, we know it's a double bond, and we know it's an oxygen atom. Think back to your chemistry last year when we were doing some work with alkenes, and think along the lines of the chemical makeup of the carbon-carbon double bond. You may remember about things like orbital overlap, you may remember about pi bonds, sigma bonds, all that kind of thing. So we're going to try and apply some of those ideas from last year to the carbonyl group, which we're going to look at this year. So you'll see that I've drawn the carbon bonded to the oxygen with a single bond. That's because we're trying to get a grip on how the double bond actually arises. So if we draw in the orbitals, the p orbitals for carbon and for oxygen, so these are both p orbitals. So it's important to also remember that the single bond between the carbon and the oxygen will also be comprised of orbitals. Obviously they'll be overlapping. So what we're looking at here is what's called a sigma bond. And that's also due to orbital overlap. So we've got pi orbitals, we've got s orbitals overlap between the carbon and oxygen to create the sigma bond. What happens when the p orbitals overlap? Well, that's when you create a pi bond. So if we redraw it on the right hand side, we can now redraw the orbitals as overlapping, but we're going to draw them slightly more towards the oxygen. Now, why might this be? Well, if we go right back to the before they actually overlapped on the left hand side, you can draw a delta plus and a delta minus. These are the dipoles, partial charges. So obviously the carbon and the oxygen have an unequal distribution of electron density between them. The oxygen is more electronegative, so it's delta minus. So you could also potentially draw the carbon-oxygen bond with the orbitals overlapping on the right hand side, like that if you wanted. Okay, the important thing is that either way you must show that there's a greater shift of the electron density on the overlapped orbitals towards the oxygen. So just to emphasize this point, I'm going to put dipoles on each of the drawn examples that I've done. So I'm always showing that I understand that it's a polar bond. So finally, what we've got to think about is when you have a carbon double bond oxygen, obviously the oxygen doesn't need any further bonds, but the carbon needs two more. So obviously you're going to have bonds coming out of the carbon. So if we do it properly, we're going to take into account the three-dimensional model. So we're going to show a wedge to show a bond coming out of the page, and we're going to show a dotted line or dashed bond to show a bond going into the page. So this bond angle should be 120 degrees, just like in alkenes. So that shows that the carbon, the shape of the bond around the carbon atom is trigonal planar, 120 degrees. So let's now look at summarising some of the facts surrounding the carbonyl bond. I have to go to a new slide for this. The first thing to remember is the makeup of the bond is very similar to a carbon-carbon double bond from last year, except this time it's a carbon double bond oxygen. So there'll be a pi bond and sigma bond, and both of these will be due to the s orbital overlap or p orbital overlap, depending on which part you're talking about. The next thing to remember is it's a polar bond, and thirdly it takes a trigonal planar shape, which means it has 120 degree bond angles. And finally, its chemical behaviour is dependent on the fact that it's polar. So these aspects of the carbon double bond oxygen should help set you up for understanding the mechanisms, the curly hour mechanisms that it undergoes, that we'll have a look at in A2.